In this publication, we discuss the experimental implementation of quantum electrodynamics with ultracold atoms. We focus on one spatial dimension and present a realization using bosonic sodium and fermionic lithium atoms. The classical empty space contains no particles, as indicated by the black box on the left-hand side. In a quantum theory, this is different. The ground state still contains no particles. However, the vacuum fluctuates permanently, which can be interpreted as virtual particle-antiparticle pairs that spontaneously appear and disappear. Whereas the ground state of an isolated system is stable, external fields may destabilize this quantum state. In quantum electrodynamics, external electric fields are able to separate the virtual particle-antiparticle pairs, create real particles, and in this way destabilize the system. This creation of electron-positron pairs out of a classical electric field is also known as Schwinger pair production, which we explain now. Even an external electric field is too weak, its energy does not suffice to account for the rest mass of the electron-positron pair. However, if the electric field amplitude reaches a critical amplitude, electron-positron pairs are generated. Schwinger pair production was first predicted in the early 1930s. However, the necessary field strengths are still beyond the reach of even the most powerful high-intensity laser facilities. In the current work, we show how a system of ultracold lithium and sodium atoms can be tuned such that it behaves as quantum electrodynamics, so that the physics of Schwinger pair production becomes detectable with current technology. Schwinger pair production is not restricted to 3 dimensions, but appears analogously in 1 dimension. In particular, lower dimensional QED is very suitable for being realizable with ultracold atoms. To this end, we employ a Hamiltonian lattice formulation a la Kogut and Susskind. The fermions denoted by psi reside on the lattice set n, while the electric field reside on the links that connect the sites. In the proposed cold atom setup, the role of the electric field is given by the angular momentum Lz, and the link variable is given by L+. The Hamiltonian can then be divided in 3 parts: the electric field energy in the blue box, the mass term in the orange box, and the interaction energy between fermions and gauge fields in the green box. We propose the following implementation of this Hamiltonian with ultracold atoms. First, the optical lattice will be red detuned for the bosons denoted by capital B, and blue detuned for the fermions denoted by F. Further, we imprint a superlattice structure for the fermions, which leads to the alternating potential energy in the orange box. Second, the interaction between the gauge field and the fermions is given by heteronuclear boson-fermion spin-changing interactions, which ensures local gauge invariance. Finally, we consider a large number of bosons, phi n, residing on each link between the fermion lattice size psi n, such that the behavior of lattice QED can be recovered. With this specific setup in mind, we determined the experimental parameters of the QED Hamiltonian. As shown, Schwinger pair production should be possible in the proposed setup. The number of created electron-positron pairs is encoded in the fermionic 2-point correlation function, which can be calculated and measured in an experiment and is depicted on the left-hand side. We observe a rapid production of electron-positron pairs, while at the same time the electric field amplitude, which corresponds to the bosonic imbalance, decreases. Once the electric field amplitude becomes too small, Schwinger pair production ceases, which can be seen in the plateau of the particle density. Finally, the presented theoretical results illustrate that engineering dynamical gauge fields with ultracold atoms is indeed feasible, and it will allow us to study phenomena of high-energy physics with tabletop experiments.